Hello everyone, my name is Theo Brito, and today I will tell you about our CVPR 2025 paper, a new statistical model of star speckles for learning to detect and characterize exoplanets in direct imaging observations. First, what is an exoplanet? An exoplanet is a planet located outside of the solar system. There are several methods to detect them, and here we focus on direct imaging. Direct imaging is a very simple method. It consists of taking a picture of an exoplanet, or rather, a series of images. This is very interesting for astronomers because it enables to analyze the spectrum of photons emitted by the exoplanet, thus providing rich information about the molecules present in its atmosphere. However, it is very difficult. The objects are so far away that it's very hard to distinguish them, and the star is much brighter than the exoplanet. Astronomers often compare this to trying to detect a firefly next to a lighthouse in New York from Paris. To do this, astronomers use large telescopes equipped with instruments dedicated to direct imaging, such as a very large telescope in Chile, coupled with a sphere instrument. And even larger telescopes are currently being built. An additional challenge when doing this from Earth comes from the presence of the Earth's atmosphere, which distorts the incoming wavefronts. This results in the spreading of the star signal into a nuisance component known as speckles, which can hide the signal of exoplanets. In order to circumvent these issues, astronomers rely on different observation strategies to unmix speckles from exoplanet signal. The first technique, known as angular differential imaging, takes advantage of the Earth's natural rotation. As the Earth turns, the sky appears to rotate relative to the telescope field of view, causing the exoplanet to follow an apparent trajectory around the target star. This motion can be used to distinguish the faint planetary signal from the stationary noise pattern associated with the star. Spectral differential imaging is another technique that leverages the physics of diffraction. The spatial extent of the speckle pattern scales proportionally with the wavelength of the filter used. As a result, speckle patterns captured at different wavelengths are related by a homothetic transformation, whereas the position of the exoplanet signal remains unchanged. This distinction allows for separation of the planetary signal from the stellar noise. Both strategies can be combined in angular spectral differential imaging, which we use in this paper. In this paper, we are exploring the use of deep learning methods to model these speckles and thus improve the detectability of exoplanets. To do this, we cannot use off-the-shelf deep learning methods because this scientific data has very specific characteristics which are very different from the natural images typically used in computer vision. For example, the quasi-stationarity of the speckle pattern, correlation across spectral channels, apparent trajectory of the exoplanet signal, symmetries in the speckle pattern, and high dynamic range. We propose to combine the flexibility of neural network with learnable components with the physical and statistical priors that we have about the data in order to design an architecture adapted to the problem. The image formation model is an additive model, and in this problem we try to recover the flux alpha of the exoplanets. The architecture of our model is guided by solving an optimization problem with two terms. The first term relates to the speckle, and the second term is a learned prior on the exoplanet signal. This optimization problem involves both learnable parameters and estimator parameters that depend on the observation. We adopt a joint spectral modeling strategy, starting by spatially aligning the speckles across wavelengths. We then exploit the hypothesis of quasi-stationarity of the speckle pattern. To capture this, we extract linear features from the aligned data and model them as samples from a multivariate Gaussian distribution. The model also incorporates features at multiple spatial scales, capturing the speckle structures across different resolutions. Another key property of the speckle pattern is its spatial symmetry, which arises from the optical design of the instrument. We incorporate this knowledge by gently modeling patches of speckle related through 180 degrees and 90 degrees rotations, effectively encoding these physical symmetries into our representation. Assuming Gaussianity, the speckle likelihood term in our optimization problem becomes a product of distributions weighted by learnable parameters omega. Crucially, this likelihood admits a closed-form solution, which can be expressed as a ratio of two sums. Each term of this sum is composed of a series of operations depending on learnable and estimated parameters. These sequences define learnable modules, which can be naturally integrated into a neural network architecture. As for the exoplanet signal prior, we use a U-net to denote the initial flux estimation provided by the speckle module, learning a representation of the planetary signal distinct from the background noise. The full architecture is trained end-to-end using semi-synthetic data, where synthetic exoplanets are injected into real observations. We optimize the model using the negative log likelihood as a training loss. Our method demonstrates competitive or superior performance compared to existing methods for detecting exoplanets in both monospectral and minispectral observations. Moreover, the interpretability of our architecture allows us to refine the estimated flux and positions of detected exoplanets by optimizing the speckle model post-detection. Finally, we present detection maps on both semi-synthetic and real datasets. These results confirm that our model reliably detects real exoplanet signal while avoiding false positives. Thank you very much for listening.